Hello everyone, myself Michael Ravina, Associate Professor, Department of Computer Science and Engineering. The subject is CS 3551 Distributed Computing. The unit is Distributed Mutex and Deadlock. In this video, we are going to discuss about Distributed Mutual Exclusion Algorithms, Introductions, Preliminaries, and Lamport's algorithm. Introduction. Mutual exclusion, that means concurrent access of processes to a shared resource or data is executed in mutually exclusive manner. Only one process is allowed to execute the critical section at any given time. In a distributed system, shared variables or a local kernel cannot be used to implement mutual exclusion. Message passing is the sole means for implementing distributed mutual exclusion. Preliminaries. The system model, the system consists of n sites, that means n number of sites. They are represented as S1, S2 to Sn. We assume that a single process is running on each time the process at site Si. That means Si is denoted by Pi. A site can be in one of the following three states. First one is the requesting the CS. Then second one is the executing the CS, or neither requesting or executing the CS. That means ideal state. In the requesting the CS state, the site is blocked and cannot make further request for the CS. In the ideal state, the site is executing outside the CS. In token-based algorithms, a site can also be in a state where a site holding the token is executing outside the CS. That is called ideal token state. At any instant, a state may have several pending requests for CS. A site queues up these requests and serves them one at a time. Requirements of mutual exclusion algorithms. First one is a safety property, then second one is a liveness property, then third one is a fairness. Safety property means at any instant only one process can execute the critical section. Liveness means this property states the absence of deadlock and starvation. Suppose two or more sites should not endlessly wait for messages which will never arrive. Fairness means each process gets a fair chance to execute the particular CS. Fairness property generally means the CS execution request are executed in the order of their arrival in the system. Performance metrics. The mutual exclusion algorithm's performance is generally measured by four metrics. First one is a message complexity, then second one is a synchronization delay. Message complexity means the number of messages required per critical section execution by a site. Then synchronization delay means after a site leaves the critical section, it is the time required and before the next site enters the critical section. This one is the synchronization delay. Here the synchronization delay is represented using the figure. Here in this figure, the synchronization delay is represented as a time. This is the last site exists the critical section between the time of last site and the next site enter the particular CS. That is a critical section. Then next one is the next performance matrix is response time. The response time is the time interval a request waits for a particular critical section execution to be over after its request messages, and that have been seen out to the following figure. Response time, the CS request time, between the particular request messages sent out and the site exit time is denoted as response time. The next one is a system throughput. Throughput means the rate at in which the system executes request for the critical section. System throughput equal to 1 divided by ST. That means system plus E. Here ST is the synchronization delay and E is the average critical section execution time. Then performance metrics. The performance metrics are low and high load performance. Already studied about the mutual exclusion performance under these two special loading conditions. They are low load and high load. The load is determined by the arrival rate of the particular critical section execution request. Under the low load condition, there is a seldom more than one request for the critical section present in the system simultaneously. Under the heavy load condition, there is always a pending request for the critical section at a side time. Next one is the Lamport's algorithm. The Lamport's algorithm is implemented using the following way. First, request for a critical section are executed in the increasing order of timestamp and time is determined by the logical clock. Every site SI keeps a request queue which contains a mutual exclusion request ordered by the timestamp. This algorithm requires communication channels to deliver messages the FIFO order. This is the Lamport's algorithm. First part of the algorithm is the requesting the critical section. When a site wants to enter the critical section, it broadcasts a request message to all other sites and places a request on request queue. That denotes here TSI, I. That means the timestamp of the particular request. When a site SJ receives a request message from the site SI, places the site SI's request on the request queue and returns the timestamped reply message to the particular site. After receiving the request, next step is executing the critical section. The site SI enters the critical section when the following two conditions are held. First one is two conditions. First one is the site has received a message with a timestamp larger than the particular timestamp from all other sites. Then second one is the site request is at the top of the request queue. These are the two conditions for executing the critical section. The next step is the releasing the critical section. After executing the particular site request, the site upon exiting the CS removes its request from the top of its request queue and broadcasts a timestamp release to message to all the sites. When a site SJ receives a release message from the site SI, it removes the SI request from its request queue. When a site removes a request from its own request may come at the top of the queue, enabling it into the critical section. The correctness of the theorem and proof of the particular Lamport's algorithm. Theorem is that Lamport's algorithm receives mutual exclusions, achieves mutual exclusion. That means suppose any one of the site enter into the critical section, means other site must enter into the same critical section, means that all the sites are sending the request message to all other sites. The proof is contradiction. Suppose two sites SA and SA are executing the CS concurrently. For this is to happen, conditions L1 and L2 must hold at both. Suppose the conditions L1 and L2 are hold by both the sites, means then this implies that some instance in the time, that means it's T, both SA and SJ have their own request at the top of their request queue, and the condition L1 holds them without loss of generality. Assume that the SA request has smaller timestamp than the request of the SJ. For the condition L1 and FIFO property of the communication channel, it is clear that at instant T, the request of SI must be present in the request queue. When SJ was executing its CS, this implies that SJ's own request is at the top of the own request queue. When a smaller timestamp request SI request a present in the request queue, this is the contradiction. Then next theorem is the Lamport's algorithm is fair. Here the proof, this is also proof by contradiction. Here same condition for SI to execute the CS, it has to satisfy the two conditions L1 and L2. Suppose this implies that some instant at time J, same own request at the top of the queue has also received the with the timestamp larger than the timestamp of, but request at the time ordered by the timestamp according to our assumption has lower timestamp. So the SI request must be placed ahead of the request of the request queue. This is a contradiction. Then performance. For each critical section execution, Lamport's algorithm requires n-1 request messages and n-1 reply messages and also n-1 release messages. Thus, Lamport algorithm requires 3 into n-1 messages per critical section invocation. Synchronization delay in the algorithm is T. An optimization in Lamport's algorithm, reply messages can be omitted in certain situations. For example, if site SJ receives the request from site SI after it has sent its own request with the timestamp higher than the timestamp of its SI's request, then the SJ need not send a reply message to the particular site. This is because when site SJ receives site SJ's request, SI receives a site SI's request with the timestamp higher than its own, it can conclude that the site SJ does not have any smaller timestamp request which is still pending. With this optimization, Lamport's algorithm requires between 3 into n-1 and 2 into n-1 messages per CS execution. Thank you.